What's up, everybody? It's me here, and let's be honest, most of us flip a switch and boom, light, like magic, right? But have you ever stopped to think about what's actually happening behind your walls, inside your phone, or powering those noise-canceling headphones? It's not magic, it's electrical engineering. And trust me, it's way cooler than trying to figure out how David Copperfield makes stuff disappear. Today, we're diving headfirst into the world of volts, amps, and circuits, breaking down complex concepts into bite-sized pieces that even your pet hamster can understand. No hamsters were harmed in the making of this video. We'll uncover the fundamental laws that govern electricity, explore the key components that make up electrical systems, and even touch upon some of the mind-blowing applications that are shaping our future. So buckle up, smash that like button for a good measure, because by the end of this video, you'll be dropping electrical engineering knowledge like a boss. Let's get electrified. First up, we've got to talk about electric circuits. Think of a circuit like a racetrack for electrons, those tiny little particles that carry electrical charge. Just like a racetrack needs rules to keep things from going haywire, electric circuits have a set of fundamental laws that govern how electrons flow. One of the most famous is Ohm's law. This bad boy tells us how much current flows through a conductor like a wire, depending on the voltage, the electrical pressure, and the resistance. How much the conductor tries to stop that flow. It's like saying, the faster you want to push those electrons through the track, voltage, and the bumpier the track, resistance, the harder it'll be to get them through, current. Now, circuits can be simple or super complicated, with multiple paths for electrons to take. That's where Kirchhoff's laws come in handy. They're like the traffic cops of the electron world, making sure everything runs smoothly, even with multiple exits and on-ramps. Kirchhoff's current law says that the total current flowing into any junction in a circuit has to equal the total current flowing out. Kind of like the principle of conservation of mass, you can't just make electrons disappear. And then there's Kirchhoff's voltage law, which states that the total voltage around any closed loop in a circuit must be zero. Think of it like taking a scenic route on the electron racetrack. You might go up some hills, voltage increases, and down some hills, voltage decreases. But you'll always end up back where you started, at zero. Understanding these laws is crucial because they form the bedrock of analyzing and designing any electrical circuit, from the simplest flashlight circuit to the complex circuitry in your smartphone. They're the tools that allow electrical engineers to predict how electrons will behave in a circuit and design systems that work safely and efficiently. All right, time to crank things up a notch and talk about electromagnetism. Now, you might think electricity and magnetism are two separate things, but they're actually like two sides of the same awesome coin. They're intertwined in a mesmerizing dance that makes all sorts of cool technology possible. Here's the deal, whenever electrons start moving, they create an invisible force field around them called a magnetic field. You've probably seen this in action with a simple fridge magnet. Those magnets have tiny electrons spinning around inside, creating a magnetic field that attracts them to your fridge. But here's the mind-blowing part. Not only can electric currents create magnetic fields, but changing magnetic fields can also create electric currents. This phenomenon is called electromagnetic induction, and it's the secret sauce behind generators, transformers, and wireless charging, basically anything that involves converting mechanical energy into electrical energy or vice versa. Faraday's law of electromagnetic induction is the key to unlocking this mystery. It tells us that the strength of the electric current induced in a conductor is proportional to the rate of change of the magnetic field around it. So, the faster you change that magnetic field, the stronger the current you get. Think of it like waving a magnet over a coil of wire. The faster you wave it, the more current you generate in the wire. Pretty neat, huh? This principle is what allows us to generate electricity on a massive scale in power plants using giant turbines and magnets. Understanding electromagnetism is like having the keys to the universe, at least the electrical universe. It's the foundation for everything from electric motors that power our cars and appliances to the antennas that allow our smartphones to communicate wirelessly. Now that we've got a handle on the fundamental forces at play, let's zoom in and talk about the building blocks of electrical systems, electronic components. These are the little guys that engineers put together like pieces of a high-tech puzzle to create everything from simple circuits to complex computers. First up, we've got resistors, the workhorses of the electronics world. They do exactly what their name suggests. They resist the flow of current. They're like the speed bumps on our electron racetrack, slowing down the flow of electrons and controlling how much current flows through different parts of a circuit. Then there are capacitors, the energy storage champs. They're like tiny rechargeable batteries that can store electrical energy and release it quickly when needed. Think of them like the capacitors in a camera flash, storing up energy and then releasing it all at once to create that bright burst of light. Inductors, on the other hand, are like the stubborn mules of the electronics world. They hate it when the current flow changes and will resist any attempts to change it. They're like the flywheels in a machine, smoothing out any sudden changes in current and storing energy in their magnetic fields. Now let's talk about semiconductors, the rebels of the electronics world. These materials, like silicon, can act like both conductors and insulators depending on conditions. This unique property makes them ideal for creating diodes, which act like one-way valves for current, and transistors, which can amplify or switch electronic signals. And finally, we have integrated circuits, or ICs, the superheroes of electronics. These tiny chips pack millions or even billions of transistors, resistors, capacitors, and other components onto a single piece of silicon, allowing us to create incredibly complex circuits in a tiny space. ICs are the brains behind our computers, smartphones, and countless other electronic devices. Understanding how these components work together is like having a superpower. It allows us to design and build electronic devices that can do everything from controlling the temperature in our homes to sending astronauts into space. All right, time to talk power. We all use electricity every day, but have you ever stopped to think about how it gets from the power plant to your phone? It's a fascinating journey that involves a delicate dance of voltages, currents, and some seriously impressive engineering. First, let's talk about the different types of currents. Alternating current, AC, and direct current, DC. AC is like a roller coaster, constantly changing direction, while DC is like a lazy river, flowing smoothly in one direction. AC is more efficient for long-distance transmission, which is why it's used in power grids, while DC is better for powering electronic devices, hence those AC adapters for your phone and laptop. Power generation is the first step, and it all starts with energy sources like fossil fuels, nuclear reactions, or renewable sources like solar, wind, and hydro. These sources are used to spin turbines, which in turn drive generators that convert mechanical energy into electrical energy, thanks to our old friend, electromagnetic induction. Once the electricity is generated, it needs to be stepped up to super high voltages for efficient long-distance transmission. This is where transformers come into play. These ingenious devices use electromagnetism to increase or decrease voltage levels without losing much energy. Transmission lines carry the high voltage electricity over long distances to substations where it's stepped down to lower voltages for distribution to homes and businesses. Finally, transformers in our neighborhood step down the voltage one last time to the standard 120-240 volts we use in our homes. Understanding power systems is essential for ensuring that we have a reliable and sustainable supply of electricity for the future. It's a complex and constantly evolving field, with engineers working on smart grids, microgrids, and other innovations to meet the growing demand for clean and reliable energy. Let's face it, electricity can be a bit of a wild beast sometimes. It's powerful and unpredictable, and if we're not careful, it can quickly get out of control. That's where control systems come in. These intelligent systems use feedback loops to monitor and regulate electrical systems, ensuring that everything runs smoothly and safely. Think of a feedback loop like a thermostat. It constantly monitors the temperature in your house and adjusts the heating or cooling system to maintain a comfortable temperature. Control systems work in a similar way, but instead of temperature, they can monitor and control a wide range of variables such as voltage, current, speed, position, and pressure. One of the key applications of control systems is in robotics. Robots rely on sensors to gather information about their surroundings and control systems to process that information and adjust their movements accordingly. Without control systems, robots would be nothing more than clunky, uncoordinated machines. Control systems are also essential in automation. where they're used to control industrial processes such as manufacturing, chemical processing, and power generation. By automating these processes, we can increase efficiency, reduce waste, and improve safety. From self-driving cars to smart homes, control systems are all around us, silently working behind the scenes to make our lives easier, safer, and more efficient. They're the unsung heroes of the electrical engineering world, taming the electrical beast and putting it to work for the benefit of humanity. In the world of electronics, information is transmitted through signals, which are basically just variations in voltage or current that carry information. Think of it like the electrical equivalent of Morse code, with different patterns of electrical pulses representing different letters, numbers, or other types of information. Now, there are two main types of signals, analog and digital. Analog signals are like smooth jazz, with continuous variations in voltage or current that can take on any value within a certain range. Digital signals, on the other hand, are like techno music, with discrete steps between values, typically represented as zeros and ones. Signal processing is all about analyzing, manipulating, and extracting information from these signals. It's like being a conductor, taking the raw electrical symphony and shaping it into something meaningful. One of the key applications of signal processing is in communication systems. Our smartphones, for example, use signal processing techniques to encode our voices and data into digital signals that can be transmitted wirelessly, and then decode those signals back into audible speech or usable data on the receiving end. Signal processing is also essential in audio and video processing, allowing us to enhance sound quality, remove noise, compress files, and perform a wide range of other audio and video magic. From medical imaging to financial analysis, signal processing plays a vital role in countless industries, helping us make sense of the vast amounts of data that surround us. It's a fascinating and rapidly evolving field with new applications emerging all the time. Chapter 7. Electrical machines, the motors that move the world. Right, time to talk about the heavy hitters of the electrical engineering world, electrical machines. These are the workhorses that convert electrical energy into mechanical energy and vice versa, making everything from electric cars to power tools possible. First up, let's talk about transformers, the voltage chameleons we discussed earlier. These essential devices use electromagnetism to step up or step down voltage levels, allowing us to transmit electricity efficiently over long distances and distribute it safely to homes and businesses. Next, we have electric motors, the muscles of the electrical world. These ingenious devices use the interaction between magnetic fields and electric currents to generate rotational force or torque. From tiny motors that power our smartphones to massive motors that drive industrial machinery, electric motors are everywhere, quietly powering our world. And of course, we can't forget about generators, the flip side of electric motors. These machines use mechanical energy to rotate a coil of wire within a magnetic field, inducing an electric current through electromagnetic induction. Generators are essential for power generation, providing us with electricity from a variety of sources, from fossil fuels to renewable energy. Understanding how these machines work is essential for designing and maintaining a wide range of electrical systems, from power grids to transportation systems to manufacturing plants. Chapter 8. Communication systems, bridging the distance with electrical whispers. Communication systems are the unsung heroes of the modern world, allowing us to connect with each other instantly across vast distances. But have you ever stopped to think about how these systems actually work? It's a fascinating journey that involves converting information into electrical signals, transmitting those signals through various media, and then converting them back into usable information on the receiving end. One of the key concepts in communication systems is modulation, which is the process of piggybacking information onto a carrier signal. Think of it like attaching a message to a carrier pigeon. The carrier signal is like the pigeon, carrying the message over long distances, while the modulation is the process of attaching the message to the pigeon's leg. There are various modulation techniques, each with its own advantages and disadvantages, but they all share the same goal: to efficiently and reliably transmit information over a communication channel. Once the signal is modulated, it needs to be transmitted through a communication channel. which could be anything from a copper wire to an optical fiber to the airwaves. Each channel has its own characteristics that affect how the signal travels, and engineers need to carefully consider these factors when designing communication systems. On the receiving end, the signal needs to be demodulated, which is basically just the reverse of modulation. This involves separating the information-carrying signal from the carrier signal and then converting it back into a usable form, whether it's audio, video, or data. From radio and television broadcasting to the internet and mobile phones, communication systems are constantly evolving with new technologies emerging all the time. Understanding the fundamentals of communication systems is essential for anyone who wants to stay ahead of the curve in our increasingly connected world. Chapter 9. Safety and codes. Respect the power. Avoid the shocks. We've covered a lot of ground in this crash course, from the fundamental laws of electricity to the complex systems that power our world. But there's one more crucial aspect of electrical engineering that we can't ignore: safety. Electricity is an incredibly powerful force, and if it's not treated with respect, it can be extremely dangerous. That's why it's essential to follow proper safety procedures when working with electricity and to always be aware of the potential hazards. One of the most important things to remember is that electricity always seeks the easiest path to ground. That's why you should never touch a live wire or electrical component, as your body can act as a conductor, allowing electricity to flow through you to the ground. Another important safety tip is to always use properly insulated tools and equipment when working with electricity. Insulation acts as a barrier between you and the electrical current, preventing shocks and other hazards. In addition to personal safety precautions, it's also essential to be aware of and adhere to local and international electrical codes and standards. These codes are designed to ensure that electrical systems are installed and maintained safely, reducing the risk of fires, shocks, and other hazards. Electrical safety is not something to be taken lightly. By understanding the risks and following proper safety procedures, we can enjoy the benefits of electricity without putting ourselves or others in harm's way. Remember, it's always better to be safe than sorry. Out to stay curious, stay charged, and there you have it, folks. We've journeyed through the electrifying world of electrical engineering, from the tiniest circuits to powerful power grids. We've seen how this fascinating field shapes our lives. From the devices we use every day to the technologies that are shaping our future. Hopefully, you've picked up some shockingly good knowledge about electrical engineering and maybe even sparked a newfound curiosity about the invisible forces that power our world. Remember, this is just the tip of the iceberg. There's a whole universe of knowledge out there waiting to be explored. So stay curious, stay charged up about learning, and don't be afraid to delve deeper into the fascinating world of electrical engineering. And hey, if you enjoyed the ride, hit that subscribe button and the notification bell so you don't miss out on our next electrifying adventure. Thanks for watching. We hope this video has given you a solid understanding of the basics of electrical engineering. Don't forget to like, share, and subscribe for more informative content.